the string will be slackened in this situation, and when arms are coming. Dear students, now you can see we are having an oscillator and a stretched string. If oscillator oscillates, then corresponding to half oscillation in the oscillator, an upper wave pulse is generated and it propagates along the length of the string. The phenomena of wave production we have just now discussed in the previous section. Corresponding to each half oscillation, a wave pulse is generated and it is propagated along the length of the string. So, students, now you can see that if the oscillator completes its one oscillation, it produces two wave pulses. One is the upper half, other is the lower half, and it is composing a wave. And this distance which the wave travels during one oscillation we define as one wavelength, which consists of one crest and one trough. So, this one crest and one trough, which is corresponding to two wave pulses, is basically called a wave. And each wave is emitted corresponding to one complete oscillation of the oscillator. Now we are going to discuss how the wave pulses forms a continuous wave train. Let's see that. Here if the oscillator continue to oscillate, we can see in this situation for continuous oscillation, correspondingly continuous wave train is produced. Wave train is nothing, just waves generated one after another. Here you can see a small particle P which is in the path of wave, which is just a particle on the string. It is just oscillating up and down, and correspondingly the wave is propagating energy in the forward direction. This is what actually happening, that every medium particle is oscillating at its own position in such a way that phase as well as energy propagates. Here you can see a tuning fork is horizontally taken along with an electromagnet attached with an alternating source. When the source is switched on, you can see the fork start oscillating, and the arms of the tuning fork will start in the direction normal to their length. So you can see it will induce transverse oscillation in the string, and here you can see there are 4 loops being formed in the string. That means the frequency of this tuning fork is 4 times the fundamental frequency of the string, or it is matching with the 4th harmonic of the string. That's why 4 loops are being produced in the string. In this situation, if we change the frequency of tuning fork, say we slightly increase the frequency, you can see if we slightly increase the frequency, the wave will start damping out and no loops are being formed. And we further increase the frequency, then at a particular level of frequency, you can see 5 loops are being formed, because now the frequency of tuning fork is matching with the 5th harmonic of this clamped string. So this is the way we can very easily understand how resonance takes place in matching of frequencies of an external source and that of a string. Here we can also mathematically analyze the situation. In this situation, just as we can see in the picture, you can see the tuning fork is kept in vertical position, and when the source is switched on, in this situation the arms of tuning forks vibrate along the length of the string, due to which the string gets slackened and then again it becomes tight, and due to this also the oscillations are induced in the string. The situation is like this. Here you can see when if there is a tuning fork and the arms are going away from the mean position, the string will be slackened in this situation, and when arms are coming close, in this situation you can see the string will become tight. So these string particles will gain kinetic energy, and when again arms will move away, the string will lose, and due to kinetic energy it will move in upward direction. So as the arm of tuning fork oscillate in a horizontal manner or along the longitudinal way of a string, the string will first get loose, then it gets tight, again gets loose. So due to this, the string will oscillate in perpendicular direction. But here you can see during one oscillation of the arm of tuning fork, the string will oscillate only half oscillation. So here we can say frequency of oscillation of a string will be equal to half of the frequency of oscillation of tuning fork. So in this situation you can see here the string is vibrating in 5 loops. So let us study some facts about direction of Earth's magnetic field. As we have already seen this picture that Earth's magnetic field is due to the rotation of iron alloy particles inside the core of Earth, due to which a magnetic field originates from the southern hemisphere of Earth and it terminates on the northern hemisphere. And the magnetic field is oriented in such a way that the magnetic axis of Earth is approximately at an angle 11 degree with respect to the rotation axis of Earth. Now in this situation, if we specifically analyze the direction at a point on Earth's surface, then in the northern hemisphere, let's consider a point P, and if we just zoom into the picture, here we can see at point P, the direction of Earth's magnetic field is getting into the Earth's surface at an angle theta with the horizontal, and if this is Earth's magnetic field BE, it will have one component BH horizontal and another component BV, that is vertical. And in this situation we can also write here that BH is the BH which is given as BE cos theta. It is the horizontal component of Earth's magnetic field, and here BV, which is BE sin theta, just have resolved into two perpendicular components. This is the vertical component of Earth's magnetic field. At different points on Earth's surface, the angle theta would be different. Here you can see at the North Pole, the angle theta will be 90 degree, and at the magnetic equator or the line where Earth's magnetic field is parallel to Earth's surface, the value of theta is 0. This theta we call dip angle, or it is also termed as angle of dip. And this is the diagram I have drawn for a point in northern hemisphere of Earth. And similarly, if I draw a diagram for southern hemisphere of Earth, then here you can see in southern hemisphere, we consider a point in this picture. Here you can see, if we zoom into the picture, you can see at a point the magnetic field is going away from the Earth's surface, B is outward, and at this point again there will be a horizontal component and there will be a vertical component with the same values, but the difference in the two situations, you can see here that in northern hemisphere of Earth, the vertical component of magnetic field is vertically downward, and in southern hemisphere of Earth, vertical component of Earth's magnetic field at any point is in vertically upward direction. And you can relate the two components as BV by BH, we can write as tan theta. That is a relation between the two components of Earth's magnetic field. And at every point, this BH you can see is in the direction from south to north, because in southern hemisphere the field is originating and in northern hemisphere it is terminating. So we can always write direction of BH at any point is from south to north direction at that point. So you must be careful about these analyses, which are quite helpful in analyzing different problems related to terrestrial magnetism, wherever you need to get the directions of different components of Earth's magnetic field. Now, just to understand the production mechanism, let's have a look on this picture, which is an atom of this anode material. And as we already discussed, that anode is made up of quite a heavy metal. That's why we can see that most of the inner orbits are completely filled with the electrons, because its atomic number is very high. And here we can see if an external cathode ray electron comes and collide with the anode, and when it penetrates into the anode atom, and if it does not collide with any of the orbiting electron, and when it comes close to the nucleus, it will experience a very high electrostatic attraction by the nucleus, and due to a very high acceleration, the electron will lose the electromagnetic radiation in the surrounding, which are actually the X-rays, and this is the way how these X-rays are produced. And we can see in this situation, according to Maxwell's theory, we know that a charged particle, whenever accelerated, it loses its kinetic energy in form of electromagnetic radiations. Let's discuss the working of a photodiode with the help of a realistic situation. Here you can see this picture shows us a PN junction which is forward bias connected through a battery, and just to measure the current in it, we have placed an ammeter in the circuit. And you can see as it is forward bias, a current I1 is flowing through the ammeter. And here we can see the junction is coated with a transparent material, and when externally light is fall incident onto the junction, suddenly continuous electron hole pair generation takes place, and the quantity of electrons and holes in conduction and valence band increases, due to which current is also increased to a value of I2. And this is because suddenly, due to excess number of electron hole pair generation, the conductivity of this PN junction diode increases and more current flows through the system. And again you can see when the light is turned off, again the generation of electron hole pair stops, and the current drops back to the dark current, which is I1. Dear students, let's discuss a realistic situation, how a light emitting diode works. Here this picture shows you a light emitting diode, and it is basically a semiconductor junction. We can zoom it and see, which is enveloped by a transparent polymer shell, and when it is connected through a battery in a forward bias mode. And here you can see a realistic LED has two terminals. One is shorter in length, other is large in length. The shorter one is connected to the N side of the junction, and the longer one is connected to the P side of the junction. Now when the switch is closed, you can see it starts glowing with a green light. And if we just zoom into the LED, we can see that there is a PN junction from which through its depletion layer continuously green light is being emitted, and it is because of continuous recombination of electrons with the holes in the depletion layer. As in forward biasing, these recombinations continuously take place, and corresponding to each combination of an electron with a hole, one photon of green light is emitted. So here we can say continuous emission of green light takes place. Similarly, such semiconductors can be used to make LEDs in which the Fermi energy gap is of the order of specific energy, which corresponds to red light of wavelength, or yellow light of wavelength, or blue light of wavelength, and corresponding LEDs will glow in various colors. So this is the way how a light emitting diode works. Here you can see there is a flat white screen on which when two parallel beams of light incident, which are having a diverging angle theta between the two beams, and on the screen when the two beams superpose, then obviously the phenomenon of interference takes place, and the alternative bright and dark fringes are obtained over here. And in this situation, this fringe width between two bright or two dark fringes can be directly written as, the string will be slackened in this situation, and when arms are coming close, in this situation you can say the string will become tight.